Good morning, everyone. It's nice to see you all here. Good morning to everyone who's virtual. I don't know where the camera is. So to get us started, I want to spend a little time talking about some work that I've been doing along with my grad student Jimmy Lin in collaboration with VEX Robotics. When we sat down to put the talk together, the initial thought was let's talk about specifically learning computer science with robotics. But then, as we talked and thought a little bit more about the opportunity that this presented to us, we decided to broaden it a little bit and think a little more broadly about our work, situating this work that we're doing in the larger landscape of computer science and K-12 education. One of the things that I think is so wonderful about this opportunity and the HCIL in general, and we heard this from Ben and Jessica just a few minutes ago, is how interdisciplinary the group is. And so as academics, we often find ourselves standing in front of people who think about the exact same type of problems that we think about. And so when you give a talk, it's this very narrow, like here, we're all talking the same frameworks, the same theories, and here's how I'm nudging it forward. But given a talk like this, where we have people coming from all these different disciplines, it's a very different setting, a very different context. And so what I want to do with this talk is, I want you guys to think about this talk as an invitation to be thinking about K-12 computer science education. So when I stand in front of a room full of educators, I put on my computer science hat and say, hey, computer science is really important, computer science ed is really important. Come think with me about what K-12 computer science can look like. When I stand in front of a room full of computer scientists or designers or iSchool graduates, it's a similar exercise, but now I'm wearing my education hat saying, there's all sorts of interesting open problems in this space. Please come and think with me about it, talk with me about it, because we need your interest and expertise. So before I get rolling, I very much want you guys to be thinking about that from this perspective, that there's all sorts of big open questions in the space of K-12 education, and having people with backgrounds in UI, UX, in accessibility, in computer science, in all the different things that we as HCIL members think about, these are the exact type of perspectives that we need to kind of push the field forward. And we have the added bonus of, so I'm going to situate all this around the work that we've been doing with VEX Robotics, and we have the opportunity, Jason McKenna from VEX Robotics, Jason, I forget your official title, so I call you the Chief Education Officer. So Jason's here and is very much, has been for us a wonderful thought partner in all this. And so if you accept my invitation to come think about K-12 computer science ed, please find Jimmy, who's my grad student collaborating on all this. Find Jason over the course of the day, because we'd love to hear your thoughts and start some conversations. Okay, so with that, let's start some conversations. So I want to start by laying a little bit of the landscape with this big picture question of what does computer science look like in K-12, across K-12 education. So at kindergarten, computer science education looks something like this. Here we have a B-bot, a Caterpillar. These are robots that have buttons on them, and the way that kids can engage with them is kind of push buttons on top, and we can see them move and things like that. And so no reading, no writing, no screens, but a way to start to engage with things like algorithmic thinking and kind of getting machines to do things you're interested in. Move forward a little bit. Now we're moseying into early elementary, middle elementary. So this is an environment called Scratch Junior. The thing to note, so this is a programming environment. It's all virtual, but what's really neat and clever about this is writing programs is based purely on symbols. So students don't necessarily need to know how to read, because we can see there's arrows and other kind of symbols and glyphs that kind of convey meaning, and students can kind of write these little stories left to right and make their little characters move across screen. And we also see a growing number of robotics environments that, again, don't necessarily require students to know how to read, but instead there's some visual ways to represent what robots do and control them. So moving forward, now we're starting to enter 4th, 5th, 6th grade. This is a Scratch environment, came out around 20 years ago and has been hugely influential in the space. I'm actually going to show you in a little more detail what Scratch looks like, because this block-based programming approach is central to the work that we're doing with VEX and a lot of work in the space. So quickly, for those of you not familiar with Scratch, here it's on the left. And so what you see is on the left is a blocks palette. So this says move 10 steps. And so I drag it in, and if I click on it, my little Scratch cat moves. And now I'm going to add a second command here that says, it's going to say change color by 10. And so now when I click it, it moves and changes. And this says repeat 10. So now when I click it, I'm getting these commands to run 10 times in a row. And finally, I'm going to drag in what we call a hat block that reads when spacebar pressed. And so now if I press spacebar, my cat moves, does the program I've executed. So a few things that's important to note. So what we've done here is we've written a program that includes multiple instructions sequentially. It contains iterative logic, so that it's going to run multiple times. We've also introduced some interaction where I hit the space bar and we get our program to execute. This was all done in about 10 seconds and did not require using the keyboard until I hit spacebar to run. So thinking about what does it mean to introduce students into practice of programming, here we have this visual, engaging, playful environment where you can do really non-trivial computing, but there's no syntax errors, there's no kind of searching for semicolons or curly braces, it's all provided visually by the environment itself. So in parallel with that, we have, again, kind of this growing ecosystem of robots. We have a Sphero robot. We have sorry, forgot what it's called for a sec, Osmo, which is starting to blend physical and virtual. So we see increasing capabilities with the robotics environments, increasing level of sophistication. Let's keep moving forward. Now we make our way up to 8th grade. In 8th grade, we were getting a new set of environments that start to blend the block-based environment that we saw with Scratch with kind of more conventional text-based programming. And so on the top left is something called EduBlocks. And so on the left, you can write and compose programs using drag and drop and blocks. And on the other side in black, you see the Python equivalent of it. So you see these two representations trying to reinforce the idea that block-based and text-based can be isomorphic. On the top right is code.org's app lab. And here we see a blocks palette where you can drag and drop. But now when you drag and drop, you're actually dropping in text. So we see blocks and text living side by side. And again, in terms of the physical computing pieces that come along with it, we're starting to see more LilyPad, Arduino, Microbit, MBOT. We're starting to see more capabilities being introduced, inviting students to work with kind of more fundamental capabilities of robotics. And then finally, we're making our way to grade 12, and then obviously onto the University of Maryland. And here we're starting to enter the world of, well, this is a Java program, a professional IDE, the robotics platforms and environments that we're using, fully featured industrial robotics kind of can do everything that robotics can do. And so that's a kind of a quick snapshot of what K-12 looks like. And so thinking about what does it look like to program representationally, we start with these symbol-based environments like Scratch Junior, and we move to these block-based environments that we are introducing some literacy and start more capabilities, environments Scratch, Blockly, Snap, and then we move on to these hybrid environments, a little bit of graphical, a little bit of text-based. There's a couple there, and then finally, by the time we get to grade 12, we're living in the world of text-based programming and a whole bunch of different languages and technologies that go along with that. In parallel to that, from a robotics perspective, we start with these press and go onto something that introduces some virtual and physical, blending those two worlds, and then we get some additional capabilities and movement and sensors, and then start to introduce microcontrollers, and then finally make our way to these industrial robots. So across K-12, what we see is we're moving from, over the course of these 12, 13 years, we're moving from symbolic-based programs, something like Scratch Junior, all the way up to kind of conventional Java, Python, et cetera. In the robotics parallel, we see something like a Bebot that's really basic. You can just kind of move it around and it can change directions, up to, right, in, powerful industrial robots kind of can do everything. And the idea is we paint the picture that this is a really straightforward path. In actuality, it's like a little more complicated. We kind of come and go. But there's a problem that underlies all this. And lucky for you guys, if you were here at the symposium a few years ago, I happened to give a talk on just this topic. So I gave a plenary, not in this room as the room next door, but I gave a talk about block-based comprehension, impact of programming representation on student performance. And what we did is we looked at how students perform. I made some last minute edits that didn't make it in, so we go. So what this chart is showing is we ran a study in a high school computer science classroom where we had one class use a block-based environment, something like Scratch. We had a second classroom use a text-based environment, something like Java. And on the first day of class, this pre-assessment, the first day of class, we gave them a computer science concept assessment, and they knew that we saw that there were no difference. They both scored about 50%. 5 weeks later, we had of one class working in blocks, one class working in text. We gave them another assessment, and we saw a significant difference. Students in the blocks condition learned significantly more than the text condition. And so this, right, blocks-based programming is productive. We should be using it. But then one of the interesting takeaways was, so then all the students moved on to Java, and then 10 weeks later, we gave them another assessment. And what we saw is, despite this divergence and one condition having learned significantly more, they converge again, which means at the end of the 15-week study, students started and ended in the same position. And our takeaway from this was, so we saw this gap emerge, but then it disappeared. And our takeaway from this, and we wrote this up in a paper, students had greater learning gains in the block-based environment compared to isomorphic text-based alternatives, but these gains did not result in a difference in the follow-on text-based instruction with respect to conceptual learning, attitudinal shifts, or successful practices. So put another way is that what we found is that all the gains that we'd identified in the block-based condition didn't transfer to the text-based. And so what that study looked like was asking a question of asking students to go from this block-based to text-based. And if you look at these are two programs that are doing more or less the same thing. And so there's this very direct connection. But now looking across K-12, we're asking that same question, but now it's moving from these two environments that look significantly different. And it's also not happening, week 5 is one environment, week 6 is the next. It's now happening across years, across grades. Likewise, the capabilities that we see students going from kindergarten to 12th grade has this really significant gap that's being traversed. Okay, so what do we do about this? How can we support this transition? I should also say there's a whole bunch of other researchers who have done similar work, and one of the recurring findings is that this transfer of knowledge from one language to the next or one environment to the next doesn't come for free. In some cases, it doesn't come at all. So there's a lot of work that needs to go along with it. So one approach, and this is where VEX comes in this collaboration, is VEX has spent the last 15, 20 years thinking about what a K-12 trajectory looks like. And so they've developed a platform called VEX 123. I'll talk about this in a little more detail. I'll talk about this in a little more detail in some following slides, but they have an environment that was designed for early kindergarten. And then they move on to a next environment called VEX Go, and we see the students moving on to these block-based environments that I just talked about, and then moving on to another kind of middle school platform that starts to integrate some blocks and text. And then from there, there's early high school that's, again, another version emphasizing the text-based programming components of it. And then finally, by the time they get to high school and beyond, they're working in a fully featured IDE. So the work that Jimmy and I here have done in collaboration with Jason and those at VEX is really thinking about the design of these introductory environments, and in particular, how we can support learners as they move from one environment to the next, particularly thinking about the kindergarten through 5th, 6th, 7th grade. And so I want to spend a little more time focusing on that. And so what does it look like to support learners as they move from VEX 1, 2, 3, these are elementary school kids, as they move on to these block-based environments, onto switch mode and then beyond. So I want to take a minute to show you what it looks like to program this environment. And so here is, and we'll have a bunch of these at the demo table, please feel free to come check them out. So there are 3 distinct ways to program, this is called the VEX 1, 2, 3, 3 distinct ways to program the VEX 1, 2, 3. The first is press and go, so it has these little arrows on it, and you can just physically push them like we saw with the B-bot and these other kind of kindergarten, 1st grade environments. The second is called a coder cards, and what we see here is we're starting to move from kind of direct manipulation, just pushing these things directly on the physical device, to something where we are now introducing literacy, we're introducing step-by-step commands, and then finally moving on to a fully virtual environment akin to Scratch, this blocks-based environment where you can send commands to the robot to follow. So very quickly, what it looks like to program in these 3 environments. So with the press and go, we, again, like the B-bot, there's buttons on it, you push them directly, and then it'll carry out the instructions. In the coder cards, we have these virtual strips that you physically put them in place, and then you can connect your coder to the robot and hit run, and it'll carry them out. And then we have our blocks-based environment. So if we wanted to write a program that said, say, move our robot forward 2 steps and then turn left, what that looks like on the press and go is there's a version where you can just hit the button on the robot itself directly, and it'll do its thing. We can also write a coder card version of it that says, at the start, drive to turn left and connect that way. And then there's a fully virtual version of this that's akin to Scratch. And what we can see is moving from a fully symbolic, no reading necessary, to a physical, no screen present, but kind of more robust, playful version of this, and then on to something like block-based. Additional features. So one of the features of blocks-based programming I've written about in other places is you can decouple the representation from the underlying kind of computational language. And so that means it becomes trivial to translate commands into other languages. So we have strips in a whole bunch of different languages. We also can have a single command do a whole bunch of work. For example, we have an act sad or act crazy that carries out a whole bunch of commands, but this opens up the opportunity for more narrative storytelling. And then in collaboration with teachers, we started to see clever ways for them to integrate things like conventional literacy practices into programming activities. Very quickly to highlight what this looks like, we conducted a study in a first and second grade classroom in a Midwestern city. We had them spend 5 sessions doing the press and go, and then another 5 sessions with the coder cards. And one of the things that we had students do was we told them the Little Red Riding Hood story and asked them to write a program to represent that. And here's a quote from the teacher we were working with. One student had this cool idea of really retelling a story. He put the house first. He drove to the house. He acted happy. Then he moved the house, and directly behind it was the wolf. And then he had it act crazy. And what was really neat about this is a student who historically has really struggled to engage academically, and was a student that the teacher had to really work with closely to try and get him to engage. But when we introduced this storytelling thing, the student got really excited and really excelled in a way that hadn't in other disciplines. The teacher also created these really neat worksheets of paper-based versions of what the coder looks like. And the thing I want to highlight here, and this gets back to the idea of supporting students across a trajectory, on the left, the student wrote their program just by drawing pictures of the symbols on the coder. In the middle, we have a student doing something that's a little bit in between, where they're writing out some commands and drawing pictures in other places. And then on the right, the student wrote out the full set of commands. And so thinking about working with first, second, third graders who are at different points along the literacy spectrum, they're all engaging in the same activity and are able to do so at a level that matches kind of where they are in terms of reading, writing, and expressing their ideas. And then across the students that we were working with, we have some quotes from students talking about how different things that they enjoyed or different parts of the coder card they were excited about, things you can slide in commands. I like the coder because if you use the robot, there's not much to do, and like there are different actions. This is talking about the capabilities that move from just press and go onto these virtual strips. We've also done some work around the switch mode, which is thinking about moving from block-based onto text-based. I'm only going to mention it here, and this is mostly just a teaser because Jimmy's going to share a little bit later a lightning talk and poster around the switch mode work, which is the focus of his dissertation, and so please look out for that. So then taking a step back to the big question that I framed in the beginning, what does computer science look like across K-12? The short answer is a whole lot, right? It's just this really diverse, exciting range of tools, environments, representations. In terms of the physical computing components of that, we can see similarly, there's all these different capabilities, different environments. And what VEX is bringing to the table and what Jimmy and I have been collaborating with them on is trying to think about what does it look like to kind of think at a higher level, connecting grades, connecting tools, connecting languages to kind of make a more seamless transition. And up to this point, we spent some time doing research, and I only shared just the tip of the iceberg in terms of what's there. First with younger grades and the coder cards. Jimmy's going to share a little bit about switch mode. But getting back to where I started is one of my goals of this talk is really to be an invitation to come and think with us about these open questions as a designer, as an educator, as a computer scientist, is all these other questions that live in this space. And some of which VEX can serve as a wonderful platform kind of doing this work alongside them. But just as a K-12 computer science education researcher, trying to recruit more interesting, smart people to the space, please come find me, come find Jimmy, come find Jason. We'd love to hear your thoughts and share more. And with that, thank you for listening, and I look forward to the conversations.